In this lesson, we're looking at extending our understanding of quadratics to include the analysis of the discriminant, and hence we're looking to solve for a variable parameter. Now, just like we did with linear, we might have a parameter m, sometimes k, which represents a series of solutions. Now, only through the analysis of the discriminant will we be able to solve for this value. So the first things first, what is the discriminant? Well, we recognize the discriminant by the symbol, the triangle, and this lies under the square root whenever we're looking at the quadratic formula. So it stands to reason then that if the discriminant is less than 0, there are no solutions. This is because we can't have the square root of something that's less than 0 on the real number field, and everything we do in methods is in the real number field. So if the discriminant is less than 0, we would be unable to calculate intercepts, and so there must be none. Now this graph here is an example of what a graph would look like if the discriminant were less than 0. So you can see there are no solutions because the turning point is positive and it's above the x-axis. Now, what would happen if the discriminant was equal to 0? Well, this means that there's just one repeated solution. Now imagine we had our quadratic formula. We said, our x-intercepts are equal to negative b plus or minus the square root of the discriminant over 2a. And we've said here that our discriminant is 0. And the square root of 0 is also 0. So if we plus or minus 0, we're saying that the x-intercept is negative b on 2a. Now you might remember this as the axis of symmetry. We're saying that the turning point is the x-intercept, and that's why we have just one solution. Finally, when the discriminant is greater than 0, this is most often the case, there are two solutions. And so if we look at a graph with what we might expect to find, usually we'd have to find the turning point, the two x-intercepts, and also the y-intercept. And if this is the case, we'd know that the discriminant was greater than 0. So, looking at a variable parameter, we're asked to find the values of m for which this quadratic equation has one solution, two solutions, or no solution. Well, we can use Desmos to illustrate why the value of m could change this graph so that it would have one, two, or no solutions. So using Desmos here, I've got a very similar graph. I'm just going to move the screen. There we are. So you can see that I've got the graph of x squared plus mx plus 1. And I'm going to vary the value of m between negative 10 and 10. So watch what happens as we change the value of m. You can see that the graph will rotate about the x-axis as such. And so there are values of m for which the graph sits entirely above the x-axis, and there are no intercepts, or rather no solutions. There are values for which it drops below, and we can clearly see 2. And there will be a point in which the turning point sits exactly on the x-axis. Now, I can manually play around with this slider so you can see where that happens. And we'll find that at the value m equals 2. So what we're saying is m equals 2 would make the value of this discriminant 0, because there'd be one solution to the graph x squared plus mx plus 1. Now on its own that's impossible to solve because there are two unknowns and there's one equation. So it's important that we look at the discriminant so that we get an answer, or an equation rather, only in terms of m. Now in between the values of 2 and negative 2, like we can see here, our graph has no solutions. There we go, we'll just balance it on 2. So in between the values of 2 and negative 2, the discriminant would be less than 0. And anything less than negative 2, we're back to two solutions. So this is why we get asked things like find the value of m or k, why we've got an introduced parameter, and it's because with a quadratic, much like a linear, the value of this parameter will determine how many solutions we have to each equation. So let's look back at our notes. It says find the value of m for which the equation 3x squared minus 2mx plus 3 equals 0 will have one solution, two solutions, and no solution. So we're not trying to solve for x. Let's say that one more time. We are not trying to solve for x. What we need to do is look at the discriminant, because regardless of what m is, and regardless of what x is, the whole equation itself will have one solution when the discriminant equals 0. So my discriminant, which is b squared minus 4ac, that needs to be equal to 0. Well, b is the coefficient of x. In this case, that's negative 2m. So if I squared negative 2m, that looks like this. And my value of a is the coefficient of the x squared term, or the leading coefficient in a quadratic. So that's going to be 3. And my value of c is that constant term, which is 3. So now if I've got my formula out here, and we work through this, we've got 4m squared minus 4 times 9, so minus 36, equals 0. Now, this is just a matter of solving for m. I'll find one solution if I've got a series of parameters for m. Sorry, what I mean to say is, I'll have one solution if we can solve this equation for a value of m. So we can do this by brute force. 4m squared equals positive 36. M squared is 9, which is if I divide both sides by 4. And m is equal to plus or minus 3. So if m equals 3, or if m equals negative 3, the turning point of this graph would be on the x-axis. And so there'd be one solution. Now what about if there are two solutions? Well, for there to be two solutions, I know that the discriminant needs to be greater than 0. So my value or my equation 4m squared minus 36, the value of the discriminant, 4m squared minus 36 is greater than 0. Well, it might seem simple to solve this by bringing the 36 over, but in fact, whenever we're dealing with inequalities and quadratics, we have to sketch the graph if we want to know the solution. So looking at 4m squared minus 36, that's going to look like this. It's a quadratic. It's dropped down negative 36 units. And I know that it equals 0 at plus and minus 3. So where is the graph bigger than 0? Well, it's bigger than 0 at all values that are bigger than 3 and all values that are less than negative 3. So to give that as my answer, m is greater than 3 and m is less than negative 3. Well, what I might say is m is such that m is less than negative 3 union with m is greater than 3. You might also give this as set notation, negative infinity to 3 union 3 to infinity. Now, this answer set is the one that I would normally use, and it's important to know that because it's less than negative 3 and not equal to negative 3, we've got our open bracket. Finally, you might be thinking, well, how could there be no solutions? And we just have to think, for what values of x is this graph below the x-intercept? Is it a negative graph? Below the x-line, I mean to say. And that's this part of the graph here. And so I can see that m is in between negative 3 and 3. Now it's important for me to give all these answers. So I would say if m is in between -3 to 3, then there are no solutions. Likewise, above in the green, if m was less than -3 or greater than 3, I would say there are 2 solutions. And in black, where m equals plus or minus 3, I'd say that there is only 1 repeated solution. And so there we have it. We've found it for 1 solution, 2 solutions, and no solutions. Now, let's use Desmos again, and I'll type in this graph. We can use a slider to see how this works. So we've sketched our graph, and we can see by varying the value of m that wherever m is in between -3, it's about there, and +3, there are no solutions. The graph is above the line, there's no x-intercepts. Because remember that this is not the graph of the discriminant, this is not that purple graph we drew over here, 4m squared minus 36. This is the graph of 3x squared minus 2mx plus 3. And so we can see that when m is exactly equal to -3, just try and get my mouse over it there. There we go. There is exactly 1 solution. Likewise, in between -3 to 3, there's no solutions, but on m equals 3, there's 1 solution. There we go. There's 1 solution. Now anything greater than 3, and we get 2 x-intercepts, or 2 solutions to where this graph equals 0. And anything less than -3, that's the same thing. So it's important to be able to visualize what our answers mean whenever we're answering these questions. So in this question, we're presented with a very similar situation. The equation kx squared equals 6x minus 3 has no real solutions. So what are the values of k? Well, instantly here, many people across the state would try to solve for k. But that's never going to work. There's 1 equation and 2 unknowns. So instead we need to create a different equation that has only k in it. And as you can probably guess, this will be done with the discriminant. The context here was that we have no real solutions. So let's first bring everything to the left-hand side and equate to 0. That is, kx squared minus 6x plus 3 equals 0. Now because we have no real solutions, we need to think the discriminant, b squared minus 4ac, is less than 0. So that is -6 squared, because that's my b, minus 4 times a, which in this case is k, the coefficient of x squared, times 3 equals 0. So 36 minus 12k equals 0. And of course I'm saying equals 0 here. What I meant to say is less than 0. Now if I brought this 36 over, then negative 12k is less than negative 36. And remember, if I'm dividing by a negative, I'll need to flip that sign. So instead of k being less than 3 here, we know that k is actually greater than 3. So here, the answer would be B. And if you weren't too sure with inequalities, you could always plug this into your calculator using the solve function. The skill is not really in solving, the skill is in recognizing that this is a discriminant question. Now, discriminant analysis can also be used in the context of points of intersection between linear lines and parabolas. So suppose I had my y1, in this case my blue line, the parabola, and that was a quadratic expression, and that equaled a linear line, my red one. So I could say y1 equals y2. If I brought everything to the left and I let it equal 0, I'd be left with a quadratic. And so I can just look at the discriminant. In this first case, if I let y1 equal y2, the discriminant must be greater than 0. Now case 2 is where my linear line just touches the parabola. which one way of saying that is that it's tangent to. So, in this case, the discriminant must be equal to 0. Finally, you'd think, how could there be no solutions? Well, it simply means that the parabola must be translated higher up than the linear line. There's no way for the parabola to randomly change direction and crash back down, and so here there'd be no solutions. So, let's start with just finding what the points of intersection are. Imagine we had y1, which happens to be my quadratic, and y2, which is my minus 2x plus 4. Finding the points of intersection is as easy as letting y1 equal y2. So, x squared minus 8x plus 12 equals negative 2x plus 4. If I bring everything to the left, so I add 2x and I minus 4, I'll end up with x squared minus 6x plus 8 equals 0. So now I've got a quadratic on the left-hand side. Suppose I wanted to factorize this. Well, if I factored this to what are the factors of 8 that add up to negative 6, that's negative 4 and negative 2, I know x minus 4, x minus 2 equals 0, so x equals 2 and 4. Now that's not actually the points of intersection, that's the x-coordinates of the points of intersection. I'll need to sub them into either one of those y's in order to find the y value. And the easiest one here would be that linear line. So my corresponding y for 2, I would say y is equal to negative 2 times 2 plus 4. So just so you can see what I'm doing there, we'll sub that in. And that's coming from this equation up here. And so I end up with negative 4 plus 4, which is 0. So the first point of intersection is 2, 0. Now I can do the same thing with the other point of intersection, the other value x equals 4. Y is negative 2 times 4 plus 4. So I'm just subbing in the 4 there, which is negative 8 plus 4, which is negative 4. So my second point of intersection would be x equals 4, y equals negative 4. Now if you sub that into our quadratic line, that would be perfectly fine and you'd still end up with the same answer. But I think it's always easiest to do it with the linear value. So suppose that we were asked to show that. Now in this case, show that is a bit like prove. So suppose we're asked to prove that the linear line y equals 1 minus x is tangent to my quadratic line x squared minus 3x plus 2. Now of course you could do this with calculus, but it would be really difficult to show that it is tangent to. Because we'd have to first say, okay, the linear line has a gradient of negative 1. Then we'd have to equate the derivative of y to be negative 1. Then we'd have to show that they are both the same point, so that the point itself lies on both lines and has the same gradient. That's not a very elegant mathematical argument. Instead, we could recognize that because one's linear and one's quadratic, that these curves will be tangential, or they'll be tangent to one another, if the discriminant of their point of intersection is equal to 0. So let's first equate them together. X squared minus 3x plus 2 is equal to 1 minus x. Now if I want to bring everything to the left, so I'll be subtracting 1 and adding x, I'll end up with x squared minus 2x plus 1. Now this happens to equal 0, so I'm able to now see how many points of intersection there are by using the discriminant. Well, my b squared minus 4ac is equal to my discriminant. So that's negative 2 squared minus 4 times 1 times 1. And so I end up with 4 minus 4, which is 0. Now in order to give my answer, I'll say, since the discriminant equals 0, these lines are tangential. And that's all you need to do. It's much, much easier than trying to use calculus to achieve the same thing. So we can see that we've spent a really long time on quadratics, but it is absolutely worth you spending the time to relearn all this stuff, because something like this could save you a great deal of time in exam 1 and would certainly be able to help you out a lot in exam 2, simply because the argument is much easier to make than if you had to use calculus. It's also really, really important to recognize things that look quadratic, and if you could maybe just make a little substitution, you could use all these methods and finally resubstitute right at the end. So what have we done with quadratics? Well, we've looked at factoring, we've looked at solving, we've looked at sketching the graph, at finding the equation. We've also looked at completing the square and using the quadratic formula. We know that we can analyze a discriminant to determine whether or not a point of intersection is tangential, or if it crosses twice or not at all. We know that we could also introduce a parameter m or k and use our discriminant to determine the values of such a parameter for which that unsolvable equation would at least have 2 solutions, 1 solution, or none at all.